Welcome back as we continue with the burning candle problem number 5 from Module 2 Investigation 4. And in the last video we had completed Part C, and we were able to represent a decrease in time spent burning of 1.8 hours on the graph. And we'll get back to that graph in a minute. Now the follow-up question to C would be Part D. How much will the length of the candle in inches change when the time spent burning is decreased by 1.8 hours? And the reference data point, we're going to go back and let this be our initial point, initial data point. So we have stopped the clock at 3.5 hours since the candle started burning, and when we measured the length of the candle at that point in time, the length was 8.3. So what if we go back in time 1.8 hours? So that's the question on our mind right now. Now I did a little summary for myself, and you might want to stop the tape at this point and just go over some of these calculations. Let's see if I can get that all in the frame. Okay. So we know from the given of the problem that the length of the candle changes at a constant rate with respect to time. So change in L is exactly negative 2.2 times change in N. And in my little chart where I'm just kind of exploring things, in green I have that given point, so this is a data point that we knew. And then in previous problems we said if we increased time by an hour, the length of the candle decreases by 2.2. So goes down to 6.1 inches. And if we further increased the time by 1 hour, we had a decrease in length by 2.2 inches. And so I think we had a data point we plotted 5.5 hours along the horizontal corresponded to 3.9 inches along the vertical. And then we started over, and this is the part C where we left off. We went back in time. So if you look, and I've gone back in time 1.8 hours, I needed to find the corresponding change in length. And when I went back in time, then you can theoretically say we've added length to the candle. And you check my calculations. If delta N was negative 1.8, delta L was 3.96, and so from green 8.3 I added aqua 3.96 and arrived at aqua 12.296. Okay, and so then to remind myself, part D, how much will the length of the candle change? We found that out. That was the change. If we decrease the time by 1.8 hours, then there'll be a change in L. That's a positive 3.96, and we got a new data point. And I've lost track of that just for a minute. But at the 1.7 hour mark, the candle was 12.26 inches long. When we went back in time, the length of the candle was more. Okay. Part E has us generalize the process we just did. And Part E asks, what is the change in the length of the candle if the candle has been burning for so many hours? Well, I didn't like the variable or the parameter they chose, so I let K hours. I let the change in N be K hours. Well, now this is no problem. We know that change in L is always negative 2.2 times change in N. And so if the change in number of hours is K, change in L will be negative 2.2K. And we have a variable or a parameter taking the place of delta N. Brings us to part F. What was the original length in the candle? In inches before it started burning. Explain how you determine this value. and then I'll let you represent that on the graph. Okay, so I'm going to go back and think about my initial data point given in the statement of the problem. And if I want to go back in time, I want to figure out back in time 0 hours since the candle was lit, what is the length of the candle? Okay. And I've written through my thinking here. Maybe this could be helpful. Okay. You might again want to stop and look at this at your own pace. Again, the question is, what's the original length of the candle? We go back to our data where we haven't manipulated the data at all. We were given this ordered pair in the statement of the problem, and we were given a constant rate, and we know how to write that relationship down. So the 2 check-marked pieces of information came from the statement of the very original problem, if you look back. Again, I want to know the original length of the candle, so my solution can be thought through. Well, how many hours passed at the point in time when none of the candle had been burned? Well, n would be 0. Also, yeah, that would be n equals 0. 0 hours since the candle was lit. We'd have the full length of the candle corresponding to n equals 0. So going back in time, we want delta n to be the final number of hours minus the initial number of hours. So that change in n, we're going back in time 3.5 hours. Change in n is negative 3.5. And now we just find the value of delta L that correlates to delta n equals negative 3.5. And this has been the same basic strategy throughout this problem. Delta L equals negative 2.2 times delta n. And if we're going back 3.5 hours, the change in the length, there's an additional 7.7 inches. So when n equals 0, the length of the candle is 8.3 plus 7.7, or 16. Okay. There was one remaining problem, part G, in your book. And it asks you on the same axis to draw the graph that represents the length of the candle in inches in terms of the number of hours spent burning. And I did a little work while I was off camera, but I was emphasizing the 3 data points for myself. I had to do a little work to get them exactly correct. But if we graphed the 3 ordered pairs, boom, 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 and then our initial 0, 16, we get 4 ordered pairs from one data point to the next. L changes at a constant rate with respect to time. L changes with a constant rate with respect to n. And if we connect, and I shouldn't have gone so far, but if we'd connected those 4 data points with a line segment, our graph is a line. And any ordered pair on the graph relates n to L on the n on the horizontal, L on the vertical axis. Thanks.